Let's review for a test for tomorrow. So we have refraction. The light coming in. It's called the incident ray. We have the normal line. We have the incident angle. And then it's going to bend toward. And we have the refracted ray. And with the refracted angle. Or we could have the reverse. This is when it's going from low to high. So low to high bends toward. So incident ray, refracted ray, going from high to low. It bends away. And then we have the special case. So this angle here is called the angle of incidence, or the incident angle. And this would be called the angle of refraction. We have the special case. That should be really a dashed line. In which case we have some special angle called the critical angle. Anything greater than the critical angle is total internal refraction. But what would this angle be? So it's going to bend away. So it'll be perfectly 90 degrees. So the angle of refraction is 90 degrees. That's how you solve for it. And you are right. Anything greater than this angle will be total internal refraction. Major equation for this is N1 sine theta 1 equals N2 sine theta 2, where this side is your incident side and this is your refracted side. Or initial versus final. So, let's do an example. Suppose I have let's say that the n is equal to 2 here, and n equals 1.25. So here is an incoming ray. It could either be straight down to the right, goes a straight line, or bend upward, or bend downward. I'll say this is A, B, C, D, E. Which of these lines is the correct path? So, is it D? So when you go from high to low, do you bend toward? So this C represents a straight line. So the angle should decrease. Here's the angle. The angle should decrease, so we can immediately rule out C, D, and E because D and E bends toward. C is a straight line, which means it has to be B or A. A is impossible. Because it's not being refracted at all, it's just going parallel, which means B is the only answer. There'll be problems like this, where I tell you you have some N1, N1, N2, N3 material like this. Light comes in, it bends down, hits, and then refracts like that. Which one has the greatest index of refraction? Or put them in the correct order. Well, we know that this has the most extreme bend, and it bends toward. So we know that N2 must be very much greater than N1. We see the angle bend away a lot, so we know that N2 is getting away, so we know N2 must be bigger than going from high to low, so this bends toward is when you go from low to high. So this must be low, this must be high, and bending away means that you're going from high to low. So that means N2 must be bigger than N3. And to see if N3 and N1, we look at which one's the more extreme. I probably didn't draw this accurately enough. Let me see if I can redraw it. Make it subtle. And then, there we go. From this example, we can see that the angle right here versus the angle right here is significantly changed. That means that we can almost rule out this middle one. And we can see that N1, or we can just ignore the middle one to compare N1 and N3. We can see that the angle has significantly changed. It's bending away. So bending away means we're going from high to low. So N1 is higher than N3. So that means we have the order is N2 is greater than N1, which is greater than N3. Make sense? Note also, like for example, let's say we have some water and some air, and you shine a flashlight at this boundary, and we're only a drill right there. So that means it's going to bend away, but also there is some reflected light. So we have some reflected light, and we have some refracted light. After the critical angle, it's all reflected. And the more straight on you are, the less reflected light you have. There's a few questions I forgot to cover. Dispersion. Dispersion is the separation of visible light into different colors. I haven't talked about polarization. It's not on the test, but I do see it as possible choices. Polarization. So remember that light is an electromagnetic wave. Some oscillation in the electrical field and the magnetic field. And that's in three-dimensional space. So this electrical field could be vibrating up and down. It can be vibrating side to side. Polarization is what direction it's vibrating up and down at. Whenever you have like a lake and sunlight is hitting it, what tends to happen is the light that bounces off of it is horizontally polarized. And you can wear some glasses that block horizontally polarized light. It's just the direction in which normal light is polarized in all different directions. But you don't really need to know that. What speed does light travel at in a vacuum? Mm-hmm. And which travels faster in a vacuum, red or blue? Which travels faster in a vacuum, red or blue? You just told me that all light travels at 3 times 10 to the...
Same thing.
Yes, they move at the same speed. So, here's another thing I didn't cover. I only have 2 questions I haven't covered. This one and this one. I don't think it's too much. But when you have, let's say, white light, then by dispersion, the redder frequencies don't refract as much, while the violet light refracts the most. When light enters a medium, its frequency stays the same, but its speed decreases. Because of the equation, velocity is equal to frequency times wavelength. If velocity decreases, this stays the same, then wavelength must also decrease. So wavelength decreases too. So which light travels fastest in the material? Red or violet?
You said violet refracts the most. said red left down, so I'll go red.
So you think red is faster or slower? Which one?
I think red's
So I'm going to confirm this before I answer it and get you confused. Yeah, I'm right. So imagine that it didn't slow down at all. Imagine that the red light did not slow down at all, right? What that means that it would so if we have, let's say, n equals something and n equals something over here, if these are the same material, let's say this is a vacuum on this side and this is a vacuum on this side, then they would move in a straight line. It'd be at its fastest possible speed, the speed of light. So the more it slows down, as this goes to like water, for example, the more this is going to want to bend. So because this bends the less, that tells you it's moving at a higher speed. Imagine there's a swing set. And we have a little kid blowing a whistle. High-pitched sound. And you're pushing this kid. At what point is the frequency the loudest of the whistle? I mean, are you sure?
No. Is it the same base frequency?
Mm-hmm. I mean, yeah, he would hear the same thing because the whistle isn't moving in respect to the kid, but you would hear constantly changing sounds.
Does it matter?
Yes, it does matter.
Like read that?
Yes. It's constantly changing. So when does the frequency get... So imagine there's a bus or a fire truck that's stationary. You're on stationary on a sidewalk. It has a frequency of 500 hertz, let's say. When would this frequency increase? When he's moving towards you, not when he gets closer. So at what point is this kid moving closer towards you? So when he gets to this highest point, what is his velocity? 0. So he has a velocity of 0 meters per second. And then he ever so slightly gets faster and faster until he reaches this point right here. And when he starts getting here, gravity is going to pull him back and stopping. What speed is he going right here? Where is he moving the fastest towards you? In the middle, right here. Another way of looking at it is, let me exaggerate this. So this is some height above the lowest point. And so he has gravitational potential energy. And then down here he has kinetic energy. And with no gravitational potential energy. So his fastest energy, or his fastest speed, I should say, is at the very bottom. Here he has no kinetic energy. Right here you have no kinetic energy. And we know that frequency increases whenever he's moving towards you. When does the whistle sound normal? only at these very 2 points. That's the point for 0 seconds, for a second instant moment in time, he's not moving. The equation for this, and I have a jumble of equations on the test. It's up to you to decipher which one goes to which, and what this means. So the equation is C plus VR over C minus Vs times the observer, or the base frequency. Remember that these values are positive if they're moving toward each other. You need to know how to apply it. What causes diffraction? Like when you shine a laser through a CD.
Oh, the slits?
It's a phenomena of what? Does it need a slit to really do it? Interference. Constructive and deconstructive interference. So, if I have a wall, and this is for multi-slit or double slit, this would correspond to a difference of 0 wavelengths. Remember that we have 2 slits that light can go through. If they both have both the same distance, the difference between these 2 paths is 0. It's the brightest spot. Right here would be whenever there is a difference of 1 wavelength. And right here is when it would be a distance of 1 wavelength too. So when this light travels 1 extra wavelength of distance, we get a bright spot. And whenever it does anything in between, it cancels each other out. We get deconstructive interference. So what would this point right here be, this dark spot? Well, this next bright spot would have to be 2, so 1.5. And this is for double slit. For single slit, yeah. Which do you think would give a better diffraction pattern? Having a longer wavelength or shorter wavelength?
Does that have a?
Mm-mm. So, again, we want to try to match up these peaks. So that we get a more brighter spot. So, technically, light and sound and any type of wave bends around corners. So, the reason why people in the hallway can hear me is because the opening, the slit, the doorway, is very big. Also, the wavelength of my sound is very large in reference to it. But for diffraction patterns, you want longer wavelength and smaller openings for it to be accurate. So if I make these super big, you would not be able to see a diffraction pattern. For example, you can't hear single frequencies outside in the hallway. You hear all the noises. You don't hear. You don't see all the frequencies break up into different colors and stuff, or sounds, frequencies. So in order to see more diffraction, should at least be obvious that we want these slits as tiny as possible. Otherwise, you wouldn't be able to see them. For example, if I took a giant big hole and shine my laser through it, obviously you would not see a diffraction pattern. Likewise, I'm trying to think of a good. Oh, here it is. So, if I have a slit and I have a little tiny wavelength, the slit would act like a giant big opening. So you wouldn't see a diffraction pattern through the slit if the wavelength is super tiny. If, however, the wavelength is very big, a lot of the wave is blocked off, and it acts like a tiny slit. So that's two ways you can get a more pronounced diffraction pattern, is by either shrinking the slit down as small as possible, or making the wavelength as big as possible. Does that make sense? I haven't covered this, but it's not really on a test. One way of thinking of light is that instead of having white light being a single wave, you can think of every single point in space as being the source of its own light. That they're constantly generating new waves, and this is called a wavefront, wavelet. So you can think of a single wave coming in as being a combination of infinite number of smaller waves, and mathematically this does work out where the crest of them all overlap to make one single crest, and the troughs and crests cancel out to where you get a true trough. This means that when going through a slit, you want the slit to be small as possible so that we get a true source of where blocking, so only one wavelength would go through. And then they combine to make a single wave. And the wave we see, this diffraction pattern, is due to the superposition of waves. So this is the principle of superposition. Whenever you have more than one wave in the same location, they basically combine together by just adding the crest and stuff to make a single wave. So you could think of a wave as being just one or a sum of infinitely number of waves. See if I can illustrate this. So can you see it? Not that one, the second one. Ah, I have it turned off.
I see one of them on the left.
Alright.
Excuse me, teachers and students, at this time, we need you to hold your students in your classrooms. Do not let anyone out in the hallway. And teachers, hold your students in your classrooms. Do not release them until we make an announcement to be released.
I'm trying to compare, and where's my red laser? I'm recording it. I'm trying to show you the difference between a red light and green light. So there's green. So I put it with a G. It gets to in between the D and T. And then if I shine my red one, so the red was somewhere over here, and the green was somewhere right here. So the diffraction pattern is bigger for the red. What do I do with these? So the red spreads more out. So red has a longer wavelength. So that means it'll spread more out. But the shorter wavelength, green, is more pronounced. Does that make sense? You can see it better, but the red one's going to be spread way more out. So illustrating that. So if you have two slits, bright spot, then we have another bright spot here. This would be for short wavelength. whereas longer ones, it'd be more blurry, be more out. So more refined point, this is n equals 1 for the short, and n equals 1 for the longer one. And they're more spread out. And while this is more defined to a single point here. So short will be something like green. Longer will be something more at red. The most shortest, of course, is violet. Out of the visible light, at least. I'm looking at the bonus. I'll give you a hint already if you want to think about it. Whenever I shine the light through the CD, how many dots were there? Is it? That's a little hint for the bonus to think about. Would it be infinite? If not, if it is infinite, that's easy. If it's not infinite, how can you calculate how many there would be? Any questions about the test tomorrow? I think I've covered every single thing that would be on the test. So it's going to cover Doppler effect, refraction, and diffraction. And I guess reflection too, but reflection is trivial.
I do gotta get surgery on my wrist.
When do you have to do that?
Mom's supposed to call and schedule it today, but we might wait till like, I think the Monday after next, because next week's my birthday. I don't wanna, have it done on my birthday with you.